Okay, so for the past several lectures, we've been discussing how to analyze and solve the homogeneous diffusion equation on the real line, and also the homogeneous wave equation on the real line. Right, so we looked at initial value problems for homogeneous wave and diffusion equation. And so what we're going to do today is extend the theory for both equations, for the diffusion and the wave equation, to the non-homogeneous problem. And so it's going to turn out that this is a little bit easier in the case of the diffusion equation, so we're going to start there, but a lot of similar ideas are going to carry over from our analysis of the non-homogeneous diffusion equation to the non-homogeneous wave equation. And in particular, we're going to see that the homogeneous theory will play a very important role, right? So we're going to be building on what we did in the last few lectures. And so, right, so let's begin with the first equation that we're going to look at today, which is the case of the diffusion equation. Right, and so I'm always saying diffusion because this is what it's typically called. But remember, you can also think of the diffusion equation as describing heat flow. Right, so sometimes you'll hear the diffusion equation referred to as the heat equation. These are the same thing as long as certain quantities in the equations are constants. Right, and in particular, we're looking at the equation ut minus some number k times uxx. This number k can have the interpretation as being like related to the heat conductivity of the material or something like that the heat is flowing through. And in that case, this does describe heat flow as well. So I'll use these terms interchangeably, as you've maybe noticed already or heard me doing already. Right, and so what we're going to do is, before we were looking at this equation when when we have 0 on the right-hand side, which is the homogeneous equation. Well, now we're going to look at the situation where we have some other function f of xt, which, well, in particular, this function f will not depend on u. Right, so it can be an arbitrary function of x and t as long as it doesn't depend on u. On whatever u is, right? And so we're going to consider the initial value problem, which is just the natural generalization of the previous initial value problem. So x is on the real line between minus infinity and infinity. And we're going to look at solutions to this non-homogeneous diffusion equation with initial condition when t is equal to 0, u is equal to phi of x. And what we're going to do is solve this IVP. Again, the main difference is that we've replaced 0 in the PDE by some other function f. And so this will take maybe about half the lecture, and then in the other part of the lecture, we'll do the same thing for the wave equation, where now we add in some other function, f of xt, instead of 0. Okay, and so before I start getting into the mathematical details, you may wonder, what is the physical meaning of this equation, right? Because remember, we derived this equation. We thought of it as describing some kind of diffusion process. We actually derived it in 3 dimensions. So imagine like a drop of dye being placed in like a 3-dimensional ball of water, and then this equation, the 3-dimensional version of this equation, describes how the dye spreads out in that ball with f equals 0, right? It was important that f was equal to 0 when we did that derivation. I think it was in the second lecture. Or the third lecture, I don't remember off the top of my head, actually. And there's a similar derivation in 1 dimensions, which we actually reviewed pretty quickly in the last Zoom meeting. Not the last Zoom meeting, sorry, the one before last. So if you go back to the recordings, you can see that, and it's also in the book. which is basically the same idea using Fick's law. And so in this case, you can think of this equation as describing just diffusion of, for example, a drop of dye, but maybe it's just diffusing in a horizontal pipe. So it's only moving left and right, right? Because it's only one dimension in X rather than 3 dimensions. Right, but for that derivation, it was also important that we also ended up with f equals 0, right? When we ran these physical arguments to derive the equations, we always got 0 on the right-hand side. So the question is, well, what does it mean to put some arbitrary function f of xt here? Right, well, let's recall from in the 1D case, which again, we discussed in one of the Zoom meetings, and you can also look this up in the textbook. So where does the diffusion equation come from? Well, imagine you have like a pipe of water, right? And say this is the left endpoint is x0 and the right endpoint is x1. And there's some substance which is diffusing in the water. Well, remember Fick's law basically says that, which is Fick's law is the main law from physics we use to find this equation. It says that if you look at the change over time of the amount of substance in the pipe, right? So in this case, well, U of xt is the concentration, right? Not the amount. So in order to get from concentration to amount, remember you have to integrate, right? So if you look at the amount, which is the integral of the concentration function, which is our solution from x0 to x1, well, this integral gives you the amount, and then if you differentiate it with respect to t, that gives you the change in the amount, right? And so Fick's law says that in the one-dimensional version, that this is proportional to the one-dimensional version of flux, which turns out to just be the difference of the first derivatives at the right and left endpoints, respectively. Right, and so this is like the flow in minus the flow out. Right, and so, well, how do you derive an equation, a PDE? Well, what you have to do to make this precise is, well, let's say this is a very tiny interval, and maybe x1 is x0 plus some small h. Right, and then so then the integral on the left is basically the time derivative of u times the length of the interval at x1, and then or at x0, sorry. And then on the right-hand side, you basically have h times the difference quotient. And so then you can divide by h and take limits, and that's where the PDE comes from, right? Because on the right-hand side, we have a first-order derivative, but if I take the difference quotient of a first-order derivative and then take limits, you get a second-order derivative, which is where the uxx will come from. And then on the left-hand side, we have a t derivative. But then how is this function f relevant for any of this? Well, imagine, we have to think back to what Fick's law is actually saying, right? Fick's law is explaining how the amount of substance changes if there's no outside interaction, right? So this is assuming no other interaction. Right, and so let's pretend that there actually is some other interaction. So let's say there's some extra source where maybe that's interacting with the diffusion. Like maybe there's like a hole in the pipe, or maybe there's something is hitting against the pipe which is disturbing the concentration, or maybe there's like a point in the pipe where more dye is being, or more substance is being put into the pipe, right? And this is affecting how it diffuses. The diffusion is no longer just described by the left and right endpoints. There's some other source that's interacting with the physical system, right? And so that's what this function f is going to be. So this f of xt is going to describe some other source, right? So Fick's law is only related to the left and right endpoints, but in the real world, maybe things are more complicated and there's other forces acting on the system, and that's what this function f is standing in for. And so if you do this like this, then, well, maybe depending on how you define f, when you take the limit, you're not going to just get dtu. So you're not going to get ut is equal to k times uxx. You'll get this plus this other function f, which is somehow adding on an extra effect. And so this is where the non-homogeneous equation will come from. Right? So you want to think of it as just the phenomenon we were describing before, which is diffusion, but with some other extra force acting on the system that wasn't present initially in the simplified picture. Right? And so in the real world, the non-homogeneous equations are more realistic because there's always some other outside stuff going on. Right. Okay, and so what we're going to do now is talk about how to describe how to solve this initial value problem. And so what I'm going to do is just tell you what the solution formula is as a theorem, and then we'll discuss like motivation for how someone would actually arrive at this formula, and then we'll prove that the formula works. Right. Okay, and so the theorem is the solution to the non-homogeneous IVP is given by the following formula. Well, this formula is going to involve this Gaussian source function, which we saw when we looked at the homogeneous IVP. And so recall that let's let S of P comma T equal 1 over square root of 4 pi kt, and then integral from minus infinity to infinity of e to the minus p squared. Or sorry, no integral, sorry. We're just looking at the source function. So just e to the minus p squared divided by 4 kt. Right, and so the solution formula will involve the source function as in the homogeneous case. And so it turns out the solution is given by, well, I have integral from minus infinity to infinity of source function at x minus y comma t times the initial condition, which is phi of y, dy. And so if you'll recall, that's just exactly the solution formula we had for the homogeneous problem. And so it turns out that you just have to add on one extra term. And so the extra term is a slightly more complicated integral, which is now integrating from 0 to t and from minus infinity to infinity of the source function also applied to the function f. Right? So I have s of x minus y. Now I also have t minus s for some other, this is going to be a lowercase s, times my other function, my outside interaction function f. Right, and so now we're integrating with respect to y and with respect to s. So you want to think of s as like a past history in time before t, and then y is just like the spatial variable, and so you end up with this double integral. And so this is the formula for the solution. And so, well, if you're given your initial condition phi, you have this homogeneous term, which is just the same as what we saw in the homogeneous case. And then if you're given your other function f, you just plug it into this formula, and that will give you the solution. Right, and so again, I said this verbally, but I should write this out. So note that this is the solution to the homogeneous problem. When f is equal to 0. And then this is like a specific solution to the non-homogeneous problem, which we're adding on. Written in like an abstract form. And so you may remember from your ODE class that when you start looking at non-homogeneous differential equations, the solutions are always given by the general solution to the homogeneous problem plus a particular solution to the non-homogeneous problem, which you would typically find through like ad hoc methods, unless you had a more developed theory. And so that's what this is, right? We have a homogeneous solution, which is the first term, and then the second term is like the solution taking f into account. And you add them together, and that gets the general solution. Right, and I just want to elaborate that a little bit further with a remark, and then we'll get into detail about where this formula comes from and how to prove it. Because if I just write down, I just wrote down a complicated integral, and so it should of course not be clear why this works or how one would arrive at this formula. So I'm gonna spend more time talking about that. But before I do this, I just want to mention that it's natural that the homogeneous solution integral will show up because, well, suppose, right, V. Well, let me just to simplify notation a little bit, let me let D denote the diffusion operator. So that's dt minus k times dxx. And let's suppose that V is any solution to the non-homogeneous initial value problem from above, meaning right, the general IVP with F instead of 0. And let's also suppose that U solves the homogeneous equation. Right, meaning U solves the equation if F is replaced by 0. Well, then what happens if I apply this differential operator D to V plus U? Well, since this is linear, this is equal to D of V plus D of U, right, because using linearity. Well, D of V is equal to F because V is a solution to the non-homogeneous IVP. But D of U is equal to 0 because U solves the homogeneous initial value problem. And so if I add on 0 to F, I get F again, right? So that means that if I add on a homogeneous term to V, I get another solution. Right, so that means, again, if I have a solution to the non-homogeneous problem, and I add on another function which solves the homogeneous initial value problem with F replaced by 0, then I get a more general solution. And so this indicates that the homogeneous solution formula should show up, right? Because we would expect you can always add it on and get a more general solution. So that's one of the reasons why we would expect this formula to be here. And then the idea is, well, we need to figure out what the other term looks like. And so that's kind of how the analysis works, is trying to figure out what should this other term be. And so one way to approach this, which is what we're going to do, is by looking at some motivation from ordinary differential equations. And so what we're going to do first is consider, this is just going to be motivation, and then I'll get back to the proof after this digression. Hopefully this will add some insight. We're going to consider the non-homogeneous ordinary differential equation, which is a direct analog of the diffusion equation. And so we're going to look at the equation briefly. Derivative with respect to t of some function u of t plus some constant a times u of t is equal to f of t, where a is a constant. And we're going to assume we have the initial condition u of 0 is equal to phi, where phi is just some constant. Later, you can imagine that, okay, let's fix x, and then that's what this sort of looks like without the x derivatives. Right. Okay, and so we're gonna review how you would solve this ordinary differential equation, and then some of the ideas will transfer over to the PDE, which is a little bit more complicated. Well, remember, you can solve this is a first order non-homogeneous differential equation, which you can solve using an integrating factor. And so in this case, the integrating factor is the function e to the t times a. Where again, a is just some fixed constant that's been given to you, maybe like a is 20 or something like that. Right, and so if I multiply by the integrating factor, I get e to the t times a u prime at t. The u prime just means the t derivative, since it's just a function of time, plus e to the ta times a u of t is equal to e to the ta times f of t. I just multiply through by this function. But now the left-hand side you can write using the product rule as the derivative with respect to t of e to the ta times u of t, right? And so that means that the derivative with respect to t of e to the ta times u of t has to equal the term on the right-hand side. And so this implies that e to the t times a times u of t is equal to some constant c by taking the antiderivative plus the integral from 0 to t of the function that was on the right-hand side, right? We're taking antiderivative, so I have to integrate. And so like e to the s times a f of s ds, right? To check this, just differentiate both sides, right? The left-hand side, I get the derivative of e to the ta times u, which is what I had here on the left. And then on the right-hand side, well, if I differentiate the constant, it becomes 0. And then if I differentiate this integral with respect to t, use fundamental theorem of calculus, you plug in t and you get e to the ta times f, right? And so this implies that my solution u of t, if I just multiply now by e to the minus ta, well, this is some number c times e to the minus ta plus integral from 0 to t of e to the minus t plus s times a times f of s ds. And maybe let me write the power of the exponent slightly differently. So it's just going to be e to the minus parentheses t minus s times a, right? Because the negative sign will distribute. And then, well, what does c have to be? C has to be, well, I need to use my initial condition, which says that phi is equal to u of 0. If I plug in 0 here, I get just c, right? Because the integral from 0 to 0 is 0. And so this tells me that this constant c had to be my initial condition, right? And so finally you get my solution u of t. Again, this is a review from ordinary differential equations, but it's important for what we're going to do. So this is equal to e to the minus ta times phi, which was your initial state, plus this other term, right? So plus the integral from 0 to t of e to the minus t minus s a f of s ds, right? And so this formula that we get here should be compared with the theorem that we're going to prove soon. Where was this? Okay, right. So remember, so for our solution to I'm claiming that the solution to the non-homogeneous diffusion equation is a sum of two terms. The first term involves the initial condition, which is phi, and it's the solution to the homogeneous problem with initial condition phi. And then the second term involves an integral of something applied to the function f, right? And so this is exactly what we have below here. So this term here is the homogeneous term, meaning it solves the homogeneous initial value problem, because if I look at derivative with respect to t, e to the minus ta phi, this does solve the original ordinary differential equation with f replaced by 0, because I just get minus a times e to the minus ta phi, which is equal to minus a times, right? Which is just negative a times the solution, which is what we have here if we set f equals 0, right? So this solves the homogeneous ODE. And moreover, if I set t equals 0, well, e to the minus 0 times a applied to phi is just 1 times phi. So this has the correct initial condition as well. So in fact, it solves the homogeneous initial value problem that we saw above. And then this is like your non-homogeneous term. And so notice that, well, I have this e to the minus ta function here, but it's just been shifted by this factor s. So it's kind of like I'm applying this homogeneous term to my function f instead of phi, but I'm doing it for all previous times and then integrating from 0 to t. And so this is, again, very similar to what we have in the theorem above, right? So this is sort of the motivation for why someone might guess that there's a formula like this. Right. And so what we're going to do is use this observation to motivate the theorem and then to actually prove that the theorem works. And so one thing I want to introduce some new terminology, which will help streamline some of the presentation. And so we're going to talk briefly about things which are occasionally called solution operators. And so a quick example, well, if we look at the ordinary differential equation that we just saw, consider the function which sends phi. Remember, phi is a constant in this case, although when we return to the PDE, it won't be. Consider the function that sends phi to e to the minus ta times phi. And let me call this, say, for example, well, this depends on t, so let me call it s of t applied to phi. Well, this is a function, and the output of the function is the solution to the differential equation. Right? So this solves the homogeneous ODE that we just saw. Right? So a solution operator is going to be a rule that transforms the initial data into the solution to the homogeneous equation. Right? So this is a rule that transforms initial data into solution to the differential equation. Right. And so, well, what's the differential equation that's actually of interest to us? Well, this is the diffusion equation. Right. And so actually up here, we really mean the homogeneous equation, right? Because this solves the homogeneous equation. So is there a rule that transforms the initial data, which is now a function phi of x, into a solution to the PDE? Well, the answer is, of course, yes, because I mean, we spent a whole lecture, actually 2 lectures, deriving this formula and proving that it works and looking at examples. We have this rule here, which is integrating against the Gaussian function or the source function. Right, and so the operator is given by, well, I take my initial function phi of x and I transform it to this integral, 4 pi k t integral minus infinity to infinity. Then I have this Gaussian term, which is the source function, and then times phi of y, right? And so this solves the homogeneous IVP with initial data phi. Right. And so this is exactly an analog of the solution operator we just saw for the ordinary differential equation. And so what I'm going to do is I'm going to define a new operator, which I'll call like a script s at t applied to phi to be this integral, right? So this is equal to this integral. Right, so it's like a rule where you input a function phi, which is why it's called, so operators are kind of like functions on functions, right? They perform some operation to a function. So for each time t, this operator, when you plug in this function phi, it outputs the solution to the diffusion equation in the homogeneous case, right? So it outputs the solution formula, right? So S of t, I don't want to confuse it with L. So st phi of x solves homogeneous diffusion equation. That's this is the solution. right? And so let's go back to the theorem that we're trying to prove. Well, if I look at the theorem, we can see that I have the solution operator here in the first term, of course, this is the homogeneous term, but I also have the solution operator in the second term. If I ignore the integral in t, let's just look at the integral inside. Well, I have my source function applied to my function f, except it's just it's just shifted over in time according to s. So this is like the solution operator at time, not at time t, but at time t minus s. And it's applied to the function f, although it may change depending on the value of s. And then this all also depends on x, right? And so what I have here is actually the solution operator showing up again, but in a slightly more complicated form in this integral. The reason I'm writing the s here is just to remember that f could potentially depend on s also. If this is too confusing, just pretend that the second parentheses aren't here, and just remember that f depends on s, right? And so the theorem, using this notation, the theorem takes the following form. Right. So the form is u of xt. Well, it's equal to the solution operator at time t applied to my initial condition phi at x. And then I have an integral from 0 to t of the solution operator at time t minus s applied to my function f at x. But then I'm integrating with respect to s, right? And so this is exactly of the same form that we saw for the ordinary differential equation, where I have my solution operator applied to the initial condition, which is the homogeneous term. And then I have an integral from 0 to t of the solution operator shifted by s applied to f of s, integrating with respect to s. That's exactly what we have here, right? And so this is like the primary motivation for why someone might guess that this formula works. The motivation is considering what happens for the ordinary differential equation and seeing if it will adapt. And it turns out that in this case, it does adapt. And so what we want to do now is actually just prove that it works, right? So proof that this works. And in this argument, hopefully you'll see why it helps to complicate the notation a little bit and introduce this notion of a solution operator. And it streamlines the proof quite a bit. Okay, and so there are two things that we have to do. So the first thing is to check the initial condition. Right, and then the second thing we have to do is check that it actually solves the diffusion equation. So what do we mean? Excuse me. What do we mean by the initial condition? Well, we want to show that if I take a limit as t goes to 0 of the formula on the right-hand side, that this is equal to phi of x, right? And so I'm just going to assume that this is continuous, which in general you can prove it is. We're going to sweep that minor issue under the rug. And so if it's continuous, then the limit as t goes to 0 is just what you get when you plug in 0. And so let's plug in t equals 0. Well, in the first term, I get the solution operator at 0 applied to phi of x. And then the second term, I have an integral from 0 to 0 of a bunch of other stuff. But remember, when you integrate from 0 to 0, it's always just 0, right? It doesn't matter what you're integrating. You're just integrating at one point, so you don't get anything. There's no area. And so while the first term is just my solution operator to the homogeneous equation. And remember that when t is equal to 0, okay, this is technically where you may have to take a limit rather than just plugging in t equals 0. But when t goes to 0, this approaches phi of x, right? So this is just going to be phi of x, right? And so this does indeed satisfy the correct initial condition, where if I take the limit as t goes to 0, I get, sorry, phi of x. Right. And so now the second thing we need to do is show that it's actually a solution to the diffusion equation, the non-homogeneous equation. Right. So I want to show that if I take time derivative minus k times second order x derivative applied to this formula, that I get f of xt. Right, and so remember, I called this differential operator, which is the diffusion equation operator, I called it, say, capital D. And so we want to show that if I apply D to U, I get f of x. Well, notice that this operator D is linear. So let's just look at this. Well, let's say I apply D to, well, the first term here is I have the solution operator at T applied to phi. And then I have the integral of these terms that involve f. Right? Well, since this is linear, I can break this up as differential operator applied to the first term plus differential operator applied to the second term, right? But the first term solves the homogeneous diffusion equation, so the first term is 0. Right? And so I just need to show that the second term is equal to f when I apply this operator. Right? And so to complete this step, it suffices to show the following. That if I take derivative with respect to t minus k times derivative, second order derivative with respect to x, and I apply this to the remaining term, that I get f, right? And so the remaining term is, how do I want to write this? Right, let me continue to use the operator notation, right? So the remaining term is, we have the solution operator at t minus s applied to the function f at x and integrating with respect to s, right? And I want to show that this derivative operator gives us f of xt, right? Because on the left-hand side, this is just the diffusion operator, and I'm applying it to the second term, right? This is the second term. And so now we just have to actually do a calculation to see what we get. So notice that I want to take the derivative. Well, let's look at the t derivative. Let's look at this term first. Well, now I'm looking at derivative with respect to t of an integral from 0 to t. But inside the integral, I have some other function of t, which is the solution operator. Right, and so this is one of the reasons why I made you suffer with all those problems involving differentiating integrals with variables in the bounds and inside the integral, because these naturally show up when you're studying, for example, the non-homogeneous version of this problem. And so we have to just use the simple application of the chain rule to find this derivative. And so it's going to be a sum of two terms. So we get, well, the first term is just going to be when you plug in t for s, right? So this is just using fundamental theorem of calculus. And so from the first term, you get solution operator when s is equal to t. So I get time 0 applied to f, s is equal to t at x. And then I get a second term, right? So this is just using the chain rule. Or like, for example, see homework 1. Right, you did a lot of calculations like this on your first homework. Plus the other term, well, the other term comes from differentiating inside the integral. So this is integral from 0 to t, derivative with respect to time of the solution operator at time t minus s applied to f. at x. Right. Okay, well, the first term, what does it mean to plug in t equals 0 into the solution operator? Or sorry, sorry. What does it mean to plug in 0 to the solution operator? This just gives you the initial state, right? And so this is just going to give you the first term, you're just going to get f of x t, right? Because just as what we saw up here, like whenever you're plugging in, when t is equal to 0, this just spits out the function you're applying it to, because it's like the homogeneous problem with initial condition phi. And so this will give you f of xt. Maybe that was confusing, so I'm going to elaborate on that point a little bit more in a second. Right, so I'll just say we'll come back, because this may be confusing if you haven't seen this before, but I'll explain this further in a second. And then the second term, well, we have the integral from 0 to t of of the time derivative of the solution operator. Well, notice that, well, for any function, the solution operator s of t applied to f solves the homogeneous diffusion equation. Right, so that's how we defined this operator s. Right, it's just the solution operator with initial condition at whatever function you're applying it to. And so when I apply this operator to f, that just means you're plugging in f into the solution formula, right, up here, right, say replacing phi by f here. But this formula is in particular, it's a solution to the diffusion equation. And so when I take the time derivative of this complicated formula, it should just be equal to k times the second order x derivative, right? So this tells you that if I take derivative with respect to t of the solution operator applied to f, this should be equal to k times second order derivative with respect to x of the same thing, right? Remember, this depends on x, right? And so this is just going to be equal to k times, or sorry, negative, right? Oh, no, sorry, positive. It's positive, that's fine. Right, so this is just going to be equal to k times the second derivative with respect to x of the same thing, right? The function doesn't change. Right, so using the fact that the solution operator solves the homogeneous PDE. Right, and so what do I end up with? Well, I end up with f of xt plus, well, I can bring out the derivative, so k times second derivative with respect to x of this term. Right, and so, well, now let me bring this integral over to the right-hand side. And so, well, notice, right, so I have this term over here. This is equal to this term over here. So if I subtract the second integral, I'm going to get the desired conclusion, right? So therefore, well, if I take derivative with respect to t of this integral of the solution operator applied to f, and I subtract k times the second derivative with respect to x of the same thing, right, I'm just bringing over the term that I start in red to the other side of the equation. Well, then all that's left over on the right-hand side is f of xt, right? This is just what we were left with. And so this says that if I apply the diffusion operator to the second term, which was this complicated integral, all we end up with at the end of the day is just f of x, which is what we wanted, right? This is what we were trying to show right here. Okay. And so that completes the proof that the formula solves the non-homogeneous problem, up to maybe this minor detail about where f came from. And so I want to like write this out explicitly because it may help you understand what's going on here. And in fact, after seeing this calculation, it may be worth rewinding to the beginning of the proof and rewatching it, because maybe you'll have a deeper understanding of what's going on here. And right, so let me call this like 2 bullet point stars. So let me add on details for some extra details for this point. Right, and so what were we doing here? Well, we were looking at the first term, which is the solution operator at 0 applied to the function f when s is equal to t at x. And so this is really interpreted as the limit as t goes to, sorry, as s goes to 0, not t. Remember, s was the other time variable, right? So this is really interpreted as the limit as s goes to 0 of the solution operator s applied to the function f at time t. Actually, that's technically correct, but what did we do here? We really set s equal t. So let me rewrite this as instead limit as s approaches t of, right, this is more in line with what we actually got, of solution operator at s minus t, or was it, sorry, t minus s, applied to f at, well, this is at time s at x. And so the point I want to elaborate on is this is kind of very compactly written. What does this actually mean? Well, this is the limit as s goes to 0 or s goes to t of, well, the solution operator is this integral involving the Gaussian, but now at time t minus s. So I have 1 over square root 4k pi t minus s integral from minus infinity to infinity of e to the minus x minus y squared divided by 2k t minus s, right? I'm replacing t everywhere by t minus s. And then I have my function f, which right, depends on s also. Right, so this is actually what we had here. And so what I'm gonna do is, well, let t bar equal t minus s, right? And so if I do that, then this becomes limit as t bar goes to 0. This becomes t bar, and this term also becomes t bar. And then s becomes t minus t bar, right? And so then as I let t bar go to 0, you can think of this as like the solution formula to the homogeneous problem with initial condition f. And so then when I take the limit, I should just get f at x, right? So this is just equal to f of x at time t, right? Right, because remember when we proved when we derived this formula that if you take the limit as the time goes to 0, you're just going to output the function that you're integrating against, and so that's where this comes from with more details. Okay, and so that's it. That's the proof of how to prove the formula for the non-homogeneous problem, and now we just know how to solve it. Right, so maybe one quick example. Right, let's say I want to find a function u of xt such that ut minus k times uxx is equal to, let's say 1. And also u of x0, the initial state is e to the minus absolute value of x. Right, so this solves the non-homogeneous diffusion equation with a f is equal to 1. And the initial condition phi is e to the minus absolute value of x. Right, well, we just have to use our formula now. So u of xt, well, we have the homogeneous solution, which is pretending that the 1 is actually a 0. And so that's the integral 1 over square root 4k pi t, integral minus infinity to infinity, e to the minus x minus y squared over 4k t, applied to phi. So e to the minus y, absolute value of y dy. And then I have the other term, which is like the forcing term, which involves this function f, which is the integral from 0 to t. And now I have my solution operator at time t minus s, right? So this is 4k pi t minus s, integral from minus infinity to infinity, e to the minus x minus y squared over 4k. Again, we're at time t minus s instead of t, and then applied to f of y comma s dy ds. Right, but in this case, f is just 1. Right, so this simplifies a little bit. This is just 1. And so we actually just get the integral of this Gaussian term, which you can evaluate if you wanted to. You should end up just getting 1 for this integral. I'm not going to do this calculation because I think it's mentioned in the book, and you'll also do this calculation on your next homework assignment. It's just going to be a change of variables. You can calculate the second term. The first integral, though, you have to leave in this abstract form. Right? This is related to the problem we talked about last lecture, where these things are typically very hard to calculate. And so you can't really simplify the first term that much. The second term you can simplify a little bit, but I'll leave the details for you'll do similar calculations on future homework assignments. Maybe that's a bit of a cop-out, but I'm sure you've heard before that math is not really a spectator sport. This is like a common phrase, right? In order to get comfortable with a lot of this stuff, you can't just watch me do it, right? You have to do it yourself. So this is a good exercise, is to evaluate this second integral, see if you can calculate it. Okay, and so now for the last part of the lecture, we're going to talk about, right, we talked about non-homogeneous problem for the diffusion equation. Now let's talk about the wave equation. Right, and so we're once again going to consider the IVP on the initial value problem on the real line. And so remember, what did this initial value problem look like? Well, I had utt minus c squared uxx is equal to 0. Now we're going to consider the non-homogeneous version. So it's going to be equal to some function f of xt. And then we had the initial conditions, right? So we had the initial position of the wave at time 0, u is equal to phi of x. And then we had the initial velocity, which is the first time derivative of the initial state, which is equal to psi or psi of x. Right? And so this is the IVP we're going to consider, and the only difference is now 0 is replaced by f of xt. Right? And it's going to turn out that the formula we get, which solves this problem, is going to be very similar in structure to the formula we had for the diffusion equation up here, except the solution operator is going to be replaced by the formula that shows up in D'Alembert's formula, basically. So it's going to look very similar. And so what I want to do first, as we did with the diffusion equation, is look at some motivation from from a certain second order ordinary differential equation. And as I wrote this, I just realized I forgot to mention, like, okay, so what is the physical relevance of this F? The F will represent maybe some outside force acting on the wave. Right, why is that? Well, recall that in the derivation of the wave equation, we use Newton's second law, which said that the acceleration, or which says that mass times the acceleration is equal to the force that's applied. I'm going to write this kind of informally. You can fill in the details if you want, or ask me in Zoom meetings or office hours to fill in the details to remind everyone where the equation came from. Well, the acceleration is the second derivative with respect to t. And then we calculated in, I think, the second or third lecture, I guess the third lecture, that the force is proportional to the second derivative with respect to x of this displacement function for the wave. But maybe there's some other force. Maybe there's some outside force that's acting. Also, like maybe the wave is not the only thing acting on itself. There's some other outside force which is affecting it. And so that's where this function f would come from. Okay. Okay, and so in order to understand this problem, let's first look at a particular second order ordinary differential equation. In this case, it helps to look at the equation while I take the second derivative with respect to t of u of t plus a squared times u of t is equal to f of t. Okay. And so once again, this is non-homogeneous. So the way you would solve this, if you think back to your ODE class, at least for the homogeneous problem, you would guess like some kind of exponential function, which may be a complex exponential. And then you would end up getting some combination of sines and cosines, which would then simplify depending on what your initial conditions are, right? So we're going to assume that u of 0 is equal to phi, which in this case will be some constant. And the initial velocity at time 0 is equal to some other constant c. Right? And so I'm not going to review completely how to solve this. I'm just going to write down what the solution is. Again, if you took a class in ordinary differential equations, you've probably seen this formula before at some point, although you may not remember it. So, right. And so, well, what is the solution? Well, it's given by some combination of sines and cosines, and then you have a term according to f. And so it works out to the following. So you have the sine of t times a divided by a multiplied by c, which is the initial velocity. And then you have cosine of t times a applied to phi. And then you have an integral that's related to the function f, right? So the integral is, well, actually, and this should remind you of the formula we looked at for the diffusion equation. You have the sine term showing up again, but it's shifted by s. And this is applied to f of s, and you integrate with respect to s. So it turns out that this is the formula to the second order ordinary differential equation listed above. Again, you would have learned this in a previous class if you studied the non-homogeneous problem. If you haven't, well, you can just check directly that this works. Just differentiate it, and you'll see that it does solve the problem with the correct initial conditions. And so we're going to use this to determine the formula. So we'll use this as a guide to solve the non-homogeneous wave equation. Why is this a good guide? Just because it's second order in t, right? It's the simplest non-trivial second order ordinary differential equation you can come up with, which is non-homogeneous also. And so here we want to look for some common terms. So notice that we have the sine term appearing. So let's consider this term. Well, so let me call this v of t. So notice that if I plug in v of 0, well, I get sine of 0 divided by a, which is 0, right? On the other hand, you can check that v of t solves the homogeneous ODE, right? So if I take the second derivative with respect to t, well, if I take the first derivative, I get a times cosine well, let me just write this out, actually, sorry. Right, so if I take v prime of t, I get, well, the a's cancel, so I get cosine when I use the chain rule. And then if I take the second derivative, I get, well, cosine, derivative of cosine is minus sine, and so then the chain rule I have to use, so I get minus a times sine of ta times c. And I can put this in this form by writing this as minus a squared times sine of ta divided by a applied to c. And well, this is just minus a squared times v of t, right? So this function v of t solves the homogeneous ODE with phi equals 0, right? And of course, well, right, so notice v prime of 0 up here. If I plug in 0, I get c, and right. Right, why does it solve the homogeneous equation? This is the same thing as u prime prime of t is equal to minus a squared u of t, right, if f is equal to 0, which is what we just saw here. The only difference is, again, f is 0, and we're assuming, the initial state, the initial condition when t is 0 is phi is replaced by 0 here, right? And so this indicates that we expect the solution formula to the wave equation when the initial position is 0 to show up, right? To show up twice, right? So it shows up in the first term here and then in the integral term. And then finally, I just want to look at the other term here, which is the cosine term. Right, so now let's consider, let me call it, say, a little lowercase w of t, which is cosine of ta times phi. You can check that this also solves the ODE, the homogeneous ODE above. And in particular, it's an easy calculation. Again, maybe pause the lecture to check this, that if I take the second derivative with respect to t, that this is minus a squared times wt. And the initial conditions are, well, w of 0 is equal to phi, and w prime of 0 you can check is equal to 0. So this solves the homogeneous problem now with c replaced by 0 and then initial position phi. Right, so we've kind of like broken up the problem into two pieces. This is like the solution corresponding to the initial velocity, and then you also have the term corresponding to the initial position, and then finally you have this term corresponding to the extra outside force F. Okay, and so we're going to use this as again, as I just said, as motivation to get the formula for the solution to the wave equation. And so what we want to think about first, notice the term that appears twice here is the term that corresponds to the homogeneous problem, or the solution operator that corresponds to the homogeneous problem where your initial position is just 0 everywhere, right? We're just pretending phi is 0. And so I'm going to define a solution operator that does exactly this, as we did with the diffusion equation. Right, so I'm going to define W, I'm going to call it like a script W applied to C at time t is equal to 1 over 2 times C times integral x minus ct to x plus ct of the initial velocity or the psi function, right? And so this is exactly the term from the D'Alembert formula corresponding to the initial velocity, right? And so in particular, I'm going to omit the calculations, but you can check pretty easily. Again, just pause the lecture and check what I'm about to write. It shouldn't be too hard. You can check that for any function, which is the initial velocity psi, if I apply the wave operator to Wt of C, this is equal to 0, right? So it solves the homogeneous wave equation. And moreover, well, if I set t equals 0, this is just going to plug out 0, spit out 0, right? Because I'm integrating from x to x. If you just integrate on one point, you get 0. And finally, if I differentiate this with respect to t, well, this is derivative with respect to t of the integral. That this is equal to just psi of x, right? So this depends on x, right, at each point. So I should maybe, right? And so this solution operator transforms the function psi into a solution to the homogeneous wave equation with, well, the initial position is 0 and the initial velocity is psi. Right? And so this should remind you of what we just saw a few minutes ago with the ordinary differential equation corresponding to the analysis in blue here, right? We had these two blue terms which involved solutions to the homogeneous equation with initial position 0 and initial velocity, the term that's showing up. And so this should indicate that there should be two terms in our solution formula which involve this operator W, right? Right, so we expect, well, my solution U of xt should be equal to this wave operator applied to C plus the integral from 0 to t. Well, we had the solution operator at time t minus s, right? So now I should be integrating at time t minus s applied to f ds. Right, so these are like the terms corresponding to the blue piece above if you use the analogy with the ordinary differential equation. And so now we just need to figure out, well, what is the term corresponding to phi, right? What is the term corresponding to the initial position? Right, and so plus a phi term, right? Okay, and so this is what the formula, again, this is only like intuitive, like motivational, where we're just sort of trying to match up with what happens with the ordinary differential equation, but it turns out to be correct. And so the theorem is the following. So the solution to the general non-homogeneous IVP for the wave equation is given by the following formula. Well, I have u of xt is equal to this wave operator applied to the initial velocity at x, plus another term which corresponds to phi, plus the term we had here. Right, and so the phi term turns out to be actually, well, it's not the wave operator applied to phi, but it's just the derivative of that with respect to t. Right. Right, and so this is the formula where how does Wt act on a function g? Again, this is a solution operator. It transforms the function g into a new function, which is 1 over 2c integral of g from x minus ct to x plus ct. Right, so this is your solution formula. Okay, so I just wanted to end the lecture, I just want to briefly comment on the remaining term, which is the phi term, and comment on how it relates to what we talked about with the ordinary differential equation. And then starting next week at the beginning of the lecture, I'll do an example and I'll show you like how to calculate using this formula, because this formula is kind of maybe abstract looking if you haven't worked with it before. Right. So what is this term here? Like why do we have the derivative of w? Well, let's go back to the original problem, which is the motivational problem, which was this ordinary differential equation. Well, notice that this term cosine of TA, which is like which corresponds to the remaining piece, which we don't understand yet which we didn't understand yet for the wave equation. Well, this is just the derivative with respect to t of the other function, right? And so if I multiply phi by sine of TA over a, this is the same thing, right? And so I can write this as derivative with respect to t of sine of TA over a applied to phi. And then this quote unquote solution operator is of the same form for all three terms, right? It's all sine of something over a times a over a, and then multiplied by another function. And so that's exactly what we did below, except you just need to have the time derivative to make this work, right? And so that's what we have here, where we have this wave solution operator appearing 3 times, except for the one term corresponding to the initial velocity, one term corresponding to the initial position, and one term corresponding to the external force function F. The only difference is that for the term corresponding to phi, you just want to differentiate with respect to t. And so I just want to, one more point to make, and then we'll be done for today, is to just point out that, and again, this is something you should check by, I'm going to write out what this is, and I think you should pause the lecture after I write this out and just double check it for yourself as practice to help you get used to these types of formulas. I claim that the first 2 terms are just the D'Alembert formula, right? So it turns out that if you look at the wave operator at t applied to c of x plus the time derivative of the wave operator applied to phi at x, this is equal to 1/2 phi of x plus ct plus phi of x minus ct plus 1 over 2c integral from x minus ct to x plus ct psi of w dw. Right, so this just reduces to the D'Alembert formula. Right, and you can check this just using fundamental theorem of calculus, right? And so you should check it yourself. Again, math is not a spectator sport, so to get comfortable with these formulas, it'll be helpful to do this calculation. And so then what we have is assuming this claim is correct, which it is. The first two terms here are just this is the solution to the homogeneous problem. And then over here we have the force term corresponding to F with the same solution operator. And so the formula looks exactly like the formula, if you recall, for the diffusion equation, where we had, over here we had the homogeneous term. And then over here we had the outside force term, right? So it's the same, the formula is actually the same. It's just that the solution operator is different. And so this is why it helps to take this slightly increase the level of abstraction a little bit and introduce these solution operators, because then the formulas for the wave and diffusion equation are of the same type. You just have to change what the solution operator is. So it makes it easier to, I think, to understand these formulas. Okay, and so I'm not gonna go through the details of the proof of this theorem. The proof is very similar to the proof in the diffusion case, so it's not worth going through it again. But what I will do at the beginning of the next lecture is just we'll begin by looking at some examples, and I'll have a little bit more to say about this. And then we're gonna move on to, we'll return to the homogeneous problem, but we're gonna look at now, instead of the domain being the whole real line, we're gonna consider the case where the domain is like a finite region, like a rectangle or something like that. And we'll discuss how to solve these equations on finite domains, which turns out maybe kind of paradoxically to be harder than solving them on infinite domains. I mean, the point is that making a domain finite adds boundary conditions, and then boundary conditions will complicate things. So this is what we'll spend most of next week talking about. Okay.